This is our first day of combination circuits, so I want to ease on into it just because I don't want to leave anybody behind. But let's just cover some of the basics. So a lot of it should be review because it was in your reading assignment. But I want to look at the basics of these combination circuits. So we got an example one right here. So this, you can see, is not a series or a parallel circuit exclusively. It's a hybrid of the two. So right here we got a parallel circuit that's in series with another parallel circuit. And so we're going to look exclusively just at how to break down to find the total resistance value. We won't go too much deeper than that just yet because I just want to kind of get the basics built up. But we're going to look at how to break this down into something much simpler to find out what the resistance totals are. So sometimes it is useful to know the equivalent resistance of a circuit that has several resistors in its network. So we're going to look at equivalent resistances, which is pretty much just an imaginary resistor that takes the place and represents a group of them to make it easier for us to solve this circuit. So the equivalent resistance is the value of the single resistor that would compromise the same load to the battery or power source. So one single resistor that would simulate the entire network of resistors is what we're going to try and break it down to, because that in theory would be our resistance total. One resistance value that represents the entire circuit. So there's a couple steps that we'll go over and how to solve that, and we'll talk about that right now. So to analyze a combination circuit, follow these steps. First, you want to reduce the original circuit to a single equivalent resistor, and we can redraw the circuit a couple times if that helps us to visualize it. And then if we have series circuits, we can add those together, and then we can use our resistance formula for the parallel circuits and break it down piece by piece. So what we're going to do is solve for the total resistance. And to do that, we can use a variety of formulas. So for the total current, once we have the total voltage and we use this method to find the resistance, we'll be able to use this form of Ohm's law to find the actual current. And then we'll have the totals for the entire circuit. So we determine the equivalent resistor voltage drops at branch currents one stage at a time, working backwards to the original circuit configuration again. So this is a 1, 2, 3, 4-step process, which makes it sound really simple here, but as you'll see, it can get complicated rather quickly. So we got a pretty simple example here. We got one combination circuit. So we have parallel resistors, and both of those branch parallel resistors are in series with this resistor here. So we could use our formula, which the one I've been typically using is this one right here. And by inputting the 8 here and the other 8 here, we can get the total. So by combining these two, we're going to get 4 ohms if you plug that in right. What you can see in the next step here is what they plugged in. So by breaking these two 8s into the formula and getting that 4 ohms, we've now made an imaginary resistor that represents this old part of the circuit. So this new imaginary resistor is in series with our old resistor that we just carried over here. And this is now just a simple series circuit. So to make this even easier, we can just simply add those two together and get a single imaginary resistor, which represents the resistance total for our original combination circuit here. So the resistance total for that is 12 ohms, which is the same as this simple resistor we used by combining these previous ones here to get this. So example 2, they have a little bit more complicated one here. But let's work through it and watch step by step how they got the information they did. So again, as you can see, we've got two 8 ohm resistors here in parallel. We're going to work our way from the outside part of the circuit with the most complicated part here and turn these into a single resistor. So by combining these with our formula, we're going to get this value, 4 ohms. Again, that's going to be the resistance total, 1 divided by 8 ohms plus 1 divided by 8 ohms, and that should give us 4 ohms. Now, when we get to this step, which all we did was by eliminating this and giving a single resistor value, now we have two series circuits that are both connected in parallel with each other. So what we can do here is pretty easy. Series, we're just going to add those values together, right? So we have 10 plus 10, and that's going to give us 20 ohms. 16 plus 4, and that's going to give us 20 ohms as well. So now we looked at how to go from here to this one, which now that's an even simpler circuit. Now we just have two resistors hooked up in parallel, which is really easy for us to solve. So again, we go back to our tried and true formula. So I got my 20s plugged in over here, and that's going to give us a total of 10 ohms, which they have represented here by pretty much back to day one, the most basic circuit that we've had. So if we look at what we started with and how we got there, we started with this circuit here, and through a series of simplifying steps and creating resistance values for internal values that were represented by the parallel and series circuits, we were able to break it down to this. And you can see each step of the way on how they got there. Once we have this is our voltage total and our resistance total right here. So once we have that, obviously we can now find out the current total. And with that, we can start working backwards, which we'll start doing tomorrow, on how to work from here back to here and find the resistance, current, and voltage totals for each individual resistor. But step one, just find the total resistance values. So we're just going to look to break all that down into one value here, and that's what we'll focus on today. All right.